Hi, everyone. Can you hear me? Cool. So thanks for attending our session today. We're going to be talking about distributed data modeling in the wild. Basically, we're both SEs, so we work out in the field. We work with customers directly. So we see how Yugabyte really works out in the real world. And that's what we're going to kind of talk about today. Yeah, I'm Jim Knicely, Distinguished Engineer at Yugabyte. This is my partner over here, Marco. He's a Senior Pre-Sales Engineer. And I'm going to start off real quickly with the fundamentals of data modeling. We don't have a whole lot of time, so it's kind of a crash course here. But you've heard today already about one of the key features of Yugabyte is the ability to auto-partition a table. So looking here, this is just a sample table holding some vehicle information. And Yugabyte will take this table and split it up into pieces. Like say this table is too big to fit on a single server, right? So now you want to distribute a database. Yugabyte's going to come along and split this up to pieces for you. And we do that by looking at the primary key of the table. And there's two pieces of the primary key. One's called the sharding key, and one's called the clustering key. The sharding key is what's important for partitioning the information. So in this case, we're partitioning on vehicle and date. And what that does is Yugabyte applies a hashing algorithm to that. And it's every time you pass the values into this hashing algorithm, it gives you the same results. It's deterministic, so we know which tablet a row is going to belong to. And in this case, there's 3 tablets. I could have pre-split this into more than that many tablets, but right now it's only 3. And then the second part of that primary key is something called the clustering key, and that's how it's ordered. So once the data is distributed to a node, it can then be ordered. And you can control the ordering here, ascending or descending. And that can be multiple columns. And what we're going to see is, so what's important about the primary key? Most of the time in the field, if a customer comes to me and says, I'm having problems with my performance of my queries, a lot of times it can be narrowed down to a change in the data model that's going to be needed. So the primary key in Yugabyte is really important. Mainly because I already talked about it, it's what distributes the data and it handles ordering for you. And the neat thing is it's index organized, right? So the primary key in Yugabyte is the table itself. So if you're able to run your queries and hit this primary key, you're going to be, it's called an index-only primary key scan. So you're scanning the table directly. If you had to create an index, you'd create an index and then go to the index and then back to the table, incurring an additional RPC hop, and that's what Marco is going to cover a little bit. But ideally, like if you look at your workload, try to tune for a primary key that's really good for your workload. And ideally, if you can't use the primary key, you're going to want to create indexes. So when you're starting to create indexes, try to include all of the columns that are involved in the where clause. And a general rule of thumb is the columns that have tighter restrictions, put them at the left side. So in this case, I'm looking at a primary key. The hash is a keyword to say hash this particular column, and this is the partitioning key. A here is a clustering key, and this is a good query pattern for if I have a where clause B equals 1 and A in some sort of range, or A is greater than some value. So this is doing a lookup on B1. B equals to 1, and then it's able to do because it's ascending and ordered by that column A, it can do the in clause really fast. There's 2 types of partitioning schemes. One's called hash, and the other is called range-based. Hash is the default, and we had kind of already talked about this. So you're basically hashing the partition column, and these are they can also be multi-column. So when you're defining your primary key, you can put brackets around or parentheses around multiple columns to build a multi-column partitioning key. And then in this case, like for instance, A comma B down there on that multi-column primary key. And then for range-based, instead of specifying hash, you specify ascending or descending. When Yugabyte was being developed, one quick story, they were looking at multiple hashing algorithms, and they kind of settled on this consistent hashing algorithm. But there's 2 different types because there's 2 different kinds of workloads, right? You're not going to have a where ID equals 1 all the time or something that simple. You could have time timestamp columns where you're going to want to do an ascending index on. These are also great if you're doing like max and mins, if you have a range-based index on that. So looking at some of the pros and cons of hash partitioning. So these are great because you can pre-split a table. So when you create a table, you can pre-split it into tablets. So you might know how big your data set is, and I have 3 nodes. I can pre-split it into 6 tablets, for instance. So as you immediately start to load data in there, it's going to be distributed automatically for you across the cluster. But we do have automatic tablet splitting, and this was mentioned in the last session by Taylor. So as it grows bigger, it's going to split for you. But these are great for, again, if it's truly distinct values, right? And it's like, so it can be fully distributed across the cluster. But a trade-off is, again, I mentioned that you have to, when you're specifying your where clause, you're going to want to specify the entire partition key in there, just so you can go directly to a tablet. If you do, if in this case, I have a partitioning on H1 and H2. The issue there is if my query has a where clause H1 equals 1 and H2 is greater than 2, that's going to cause a fan out, and it's going to hit more than one tablet. So ideally, you could have an index on H1, H2, make sure H2 would be ascending here. It would be a clustering key versus a partition key. And then for hashing, again, just make sure that you choose a good key that can be distributed, right? So you have many distinct values. And a general rule of thumb there is the distinct partition count. So if you look at all your partitions, the distinct counts for those should be an order of magnitude bigger than the number of tablets, and that'll give you the best performance with hash-based partitioning. Now, range-based partitioning, again, are great for if you have a where clause that says this column is greater than something or is in between these 2 values. And it's also great if you have an order by clause on the column. And this is more Postgres compatible, so this is the default for Postgres. But the trade-off of this is that Yugabyte doesn't know the split bounds in the beginning, right? Because it's a timestamp. You don't know the beginning and an end. When you're doing the hash, the range is known. The range of the hash is from 0 to 65,535. And then when you split that up into multiple pieces, its ranges that are known. Because I have 6 tablets, it's just divided by 6. But when you have this ascending or this kind of partitioning, it's really difficult to start off with. So it typically starts off with 1 node. So you're not really pre-splitting this. But again, we have automatic tablet splitting. This was kind of an issue when it first came out because we didn't have automatic tablet splitting. So we'd have to create another index later on. But now you can just let automatic tablet splitting take care of it for you. So it's not much of as big of a deal as it used to be. And then, I'm going to pass it over right now to hear a use case from Marco.
Thank you, Jim. Can you guys hear me okay? No? No? I could talk louder too. Either works. Okay. Yeah, thank you. So Marko Rajcevic at SC that works with Jim, helping cover a lot of our accounts. I have the pleasure of talking about our first use case today. This is a visitor relationship management platform that utilizes Yugabyte DB Eon to build an IAM service for publishers to better engage with their audience. So here we're storing generic logins, accounts, metadata, sessions, especially with the importance of first-party data these days. Allowing publishers to have access to this data is becoming extremely important for them to engage with their audience in the right way. So 2 key requirements here. One is distribution of data for low latency. How do we improve the read latency that these users are going to have available to them? And the easiest way to do that is moving data closer to those users. And the second one is high scalability. Now that our users have low latency, how do we make sure that we can continue to serve them with low latency as both the traffic for the VRM itself as well as its customers continues to grow? So topology-wise, they're running what we refer to as a stretch cluster, meaning a single primary cluster that covers 3 separate regions in the United States. You can see that outlined in the orange over here. Yeah, and then outside of the primary cluster, they have 5 separate read replica clusters. And these allow them to extend that data in a read-only fashion to further away geos like Europe, like Asia, to serve some of that low latency reads. And each one of these regions is completely homogeneous when it comes to their application stack, meaning it's the same microservices running. The only real difference is varying scale. Obviously, you're going to have some regions that are more popular than others, especially as you first start to expand globally. And one of the things that they're doing, especially in the read-only regions, are using what we refer to as follower reads to serve some of that low latency read needs in those regions. So when it comes to how they started tackling their data model, first goal of theirs and the main goal is really how do we make most use of our primary key? We want 90% of our queries to be against that primary key. Why? It's the most efficient way to get to your data, right? And an example of this is, if you're selecting columns in your where clause, whether your primary key is made up of a single column, multiple columns, you want to be able to use all of them in it to most efficiently get to that data. And at the very least, if you don't want to use all of the primary key, if it has multiple columns, you just want to make sure that you're using your sharding key. Because that's, especially in the hash, when you're hash sharding your tables, that's going to be the most efficient way to get to that hash. And the second is using natural keys instead of synthetic keys. And a lot of this has to do with the fact that when you already have an existing column in your schema, your application is probably much more likely to actually use that. We good? Is that working a little better? I feel like I can hear some improvement. Yeah, okay, I'll stop screaming. Yeah, so anyway, use natural keys instead of synthetic keys when you can. An example here, table logins, auth ID, we're using that as a primary key in this example, but we also have the columns auth email as well as text. We also have a unique index on auth email. However, 90% of my queries are actually to auth email and not using auth ID. So that means every time that I have a query on auth email, well, we're gonna have an RPC to the index as well as the main table. So how do we eliminate that extra RPC? Well, if 90% of your queries are using auth email, it's a natural part of that schema, you should just go ahead and use that as your primary key instead. So not only is it important to have a primary key that's efficient, it's also really important to use that primary key as much as possible. And then lastly, high cardinality. You really want high cardinality for effective sharding keys. And the goal here is how do we scan the least amount of rows as possible? If you have a primary key like this one, let's say your primary key is ABC, where A is something like auth type that has only a few values. You know, if you're going to be querying by A, auth type in this case, there's going to be a lot of rows you're going to have to scan through. So changing that to something like AB and hashing those two values together is going to be the better option, because the likelihood of a row only having, or only one row having a combination of A and B is going to be higher. So with the primary key focus, whether it's a table or an index, the goal here really is to scan the least amount of rows as possible. Next, so covering indexes. A covering index is an index that includes all of the columns that you need out of that your query needs. And the key here is just how do we perform index-only scans, where you want to just be able to go to your index to serve the entire query and not have to send an RPC to the index and then send another RPC to the table. So if we take this query, by example, select auth ID, auth type from logins, where auth email equals mreitrich@yugabyte.com. Pretty simple query, right? But in this case, if we're creating an index just on auth email, it's still going to be super effective. But you'll see here that there's an RPC request for both there's a table read request and an index read request, right? If you were to create a covering index, meaning it's the same index, we're just using the include clause and adding auth ID and auth type because that's what we're selecting for, you'll see that that now gets us down to just a single index read request. You can also see in the query plan that instead of an index scan using that index, we're using a index only scan. So covering indexes are a super powerful tool. Second, co-locating your tables. So in Yugabyte, by default, as Jim said, we're splitting up each table into X amount of shards, and we're distributing those shards across the nodes of the cluster. This is very useful for tables that you know are going to continue growing and having more and more data. In cases where this is not the case and you want to continue to eliminate RPCs, especially multi-region setups where we might be talking about two regions that are further apart, we might want to co-locate those tables. So instead of
taking each table and breaking it up into pieces. What we're doing is we're combining multiple tables into one shard. And by doing that, we're going to be avoiding some of those additional trips across the network. Now, one key thing to call out here is even though we're co-locating these tables, we're still replicating these tables across the cluster, meaning that the fault tolerance that is built into Yugabyte using the wrapped protocol is still there. We're just doing it multiple tables in that single tablet that is then replicated. So an example here, basic select from logins onto account logins. And in a situation where you have a non-collocated table, we're running at about 1.3 seconds, right? Versus in a collocated table, you'll see that the actual query plan is pretty much the same outside of the fact that one execution time is a bit faster. So this one's a little bit under 1.1 seconds. We're using some less memory as well. So in situations where you can, collocation is another unique tool that you can use to improve upon some of your latencies, especially in multi-region scenarios. And then lastly, avoiding hotspots when choosing a primary key. And this is more of an issue when you're doing range sharding than it is for when you're doing hash sharding. But hot shard's a common problem when you have one shard that's a lot more active part of the table than the other pieces to it. And a lot of this too is if you're evaluating your CPU usage, if you see that one node is running at 60, 70%, whereas your other nodes are running at 30, 40, that's typically a good indicator that, hey, I might want to take a look at how I'm sharding this table or index, because clearly there's one shard that's more active than the rest. So an interesting way to approach this, especially for your range queries, right? Typically you want to range shard with range queries. We want to prefix it with a low cardinality hash value and then use range sharding on that. So if you take a look at this query, select star from logins where updated at is greater than some timestamp, this is going to run really efficiently using this column, right, for reads. So reads aren't necessarily going to be the bottleneck here, but the bottleneck becomes the writes, because now every time you write to this table, there's going to be one particular shard that's going to be constantly active because you're always updating the latest updated at column. So what we can do here is we can actually use a built-in function to Yugabyte called YB hashcode that will allow us to kind of, in a way, combine hash sharding and range sharding the same way. And really what we're doing here is we're using this hash function on updated at, and then we're modulating it to create smaller buckets that we can then split across the cluster. And the real reason I'm using 3 here is simply because in this scenario, let's pretend we have a 3-node cluster and we want one bucket and one tablet per node. That's it for that one. If you want to.
So that YB hash code function he just showed you is exactly what I'm gonna have both on. Can you guys hear me? Okay. That YB hash code function is actually, it uses the same algorithm that we use whenever you create a table in a partition, that it uses the same algorithm for that. So it's kind of neat that you can use this function to look up smaller pieces of a table. I do this trick all the time where you say, select asterisk from table where the partition key is between 2 different partition values that come back from that function. So say you're doing a count on a table that has 1 billion rows. That doesn't work so well in the distributed database, but you can break it up in these tiny little pieces and then sum it all together. But that's a cool little feature. So what we're getting at here is in a distributed system, how do you limit the number of RPCs? How do you limit these network hops? That's kind of the story we're trying to give to you. And it's all these tricks that we've learned over time. So this is one of my favorite stories to tell. I think for this case, we used almost every trick I could think of to get the best performance for them. So this use case it's a logistics company. It's not Amazon, but they're kind of like Amazon. And what they're doing is, this is a warehouse use case. So these guys have this RF gun and they're scanning whatever's being shipped. And once they scan it, there's a whole bunch of activities they have to do on their gun. Like I think there's 13 to 15 clicks on there. But these guys, when they did it, I was given a demo of how they did it, and they would, they click really fast, and they'd be done in, 2 seconds of these 15 clicks. It's kind of like how we use our cell phones. So you can't have any latency because every time they do a click, it's going back to some master database to get authentication to see if this user has access to the next step that he's trying to do. So we needed a low latency read there. And then it's also writing out information too, but this information is being written to a temp table. So this particular use case was great for these little tricks that we're going to learn about here. So what they wanted was, they wanted to keep the low latency that they have with the current database, but they didn't have any resilience. We joked this morning about how many times you're going to hear the word resilience today, but that's what they wanted. They knew that their data, these are physical data centers, and they had failures with these physical data centers, and they knew it was going to happen again. So they wanted some resilient solution to come in and try to help avoid any downtime. So this is kind of what we did for them. Here, there's 3 regions. You heard earlier about, Taylor talked about having these fault domains, so you have to have 3 fault domains. This is a replication factor of 3 database, so every one of these regions has a copy of the data in some circumstances. But region 1 and region 2 are physical data centers in east and west, and you can see the latency between the 2 is 20 milliseconds. And to get them to a spread cluster, we needed 3 fault domains. They didn't have a 3rd physical data center, so we used the cloud just as an onlooker, right, to make sure the quorum is there. So the Azure region never did any work in this use case. It was always region 1 and region 2 doing all the work. So what they did was, there's application users on both sides. So region 2 is a warehouse. Well, it's a bunch of warehouses. Region 1 is a bunch of warehouses. And these app users are inside the warehouses clicking away on those RF guns. So what we did was they needed super low latency reads. And Yugabyte has a feature called latency optimized geopartitioning. And what that is it's controlled by table spaces. If you're familiar with Postgres has table spaces. Table spaces are typically used to locate data on disk, for instance. We inherited this feature, but we kind of hijacked it, and we're using it now to place leaders. When Taylor was talking earlier, he mentioned the peer group, right? So there's a leader and 2 followers in an RF3 cluster. We can control where that leader resides, and the leader is the one that's responsible for reads and writes. It does all of the I/O, unless you have follower reads turned on, and then the followers can do reads. But for this case, we wanted to put the leader for tables assigned to this table space in a particular region. So if you look at the syntax here, so it's just create table space, and then there's a replica information. We're saying I have 3 replicas, but I want 1 replica in PDC, 1 in FDC, and 1 in Azure. But I want the leaders for all of these tablets to be in PDC, and we did the opposite for FDC. So basically all the tables in this table space, all the reads are going to occur in the region where the table is located. So this gave them very low latency reads, right? Because there was 3 nodes in each region. So the difference between the AZs and actually in the data centers was super fast as far as the reads. So this is one of the features for that. But there was another case where certain tables, and this is the cool thing, is you can target a table and an index to whatever you want it to do. So for a different set of tables, these are kind of like temporary table-ish, where they were going to be doing writes, but it didn't need to be super highly available. So doing the writes within the region, and if the region had failed, it would be okay. But they wanted a really high rate. And this is that authentication piece. They received an authentication token, but they needed to write it out to these temp tables. So what we did for that is something called locality optimized geopartitioning. It's kind of the same concept, except this time we're now putting all of the replicas in a fault domain. So there's a table, and again, this is all based on table spaces. So we created a single region, we called it single region. A table space for PDC, a single region table space for FDC. And here you can see I'm saying put all of my copies into that particular region. So when it does a write, it's now writing just to that location. It's also doing all the reads from there. And again, this is, you don't want to do this for all your tables because you're losing resiliency, right? But if you have certain use cases where it's not necessary, this is a great feature. This is also good for GDPR, but we kind of stole it and did it for this concept. And then one of the things they told me in the beginning was we didn't want to do any application rewrites, right? This is Postgres. They just want to move it over to Yugabyte. They want all these features, but they don't want to change the application. So whenever you introduce these table spaces, you have to add a column to the table, and that column value is going to be the region where the row is located. So it gives Yugabyte a way of figuring out where the row is. So we added a column called DC for data center to the tables involved that needed this feature set. And what you do is you set the default equal to this function called YB server region. And that is a helper function. There's actually there's a YB server zone and a YB server cloud, but it tells you when you query that where you are. So when they insert data into this table, it'll automatically be populated with that region, which is perfect, right? So now they don't have to change the application because they were concerned they're going to change all of their insert statements, but they didn't. All the insert statements work fine because of this. And then when you create the table, again, you have to specify the table space and then for values in if you know how these work. So basically, the test GeoPDC table will query all data in PDC. The test GDFDC will query data in the FDC. And then to continue on, we don't want any changes. For partitions to work, you have to have a where clause. You have to say where this region column that we added, where it equals some value. So to overcome that, where they didn't want to have to change all of their SQL statements, there's another feature called row level security. And this is neat that you can, per table, you can apply a security policy to automatically attach a where clause to every query that hits this table. In this case, it's down the bottom there. It says where DC equals YB server region. And remember, YB server region equals the region that you're in. So whenever you query this table from FDC, for instance, that'll equal FDC, and then automatically going to apply where DC equals FDC. So they didn't have to change the application for that. And then this is probably one of my favorite features of Yugabyte. It's called, it builds on the covering indexes that Marco talked about, but these are called duplicate covering indexes, where in this case, we have a covering index, but we're duplicating it in each of the regions. And the reason we want to do that is if we want really fast reads of just this information, right? So the information here will be queried locally on whatever region it is. And the optimizer is smart enough to know, hey, I have this index here. So this is a really cool feature for that. But you have to be careful with these because you're duplicating the index, so a write is going to incur a heavier write. So it depends on your workload. If read is more important to you than the write for a particular table, these are awesome. But don't get carried away with creating too many of them. And then follower reads. We didn't want to, you can enable follower reads for the entire database. Not a good idea, but you can do it at the database level, at the user level, at the session level, but you can also do it at the function level. So these guys had, for every insert, update, and delete, they had a built-in function, and they did that to abstract that layer away from the application developers. They didn't want them building their own insert statements or update statements. So they have a function. Here's an example of a select function. And all you have to do is embed these two little set commands to make this function use follower reads only, right? So as soon as the function ends, follower reads turns off. So this is a pretty cool little feature. And again, you can target, we were able to target everywhere we wanted this to happen, again, with no application changes. And as a result, this is kind of how it turned out with Postgres. At the end of remember I talked 13 to 15 different steps. At the end there was a particularly heavy write and read that happened, and in Postgres it was 102 milliseconds. But using these tricks, we could do it at 43.7 milliseconds. But we gave them better performance, and we also gave them resiliency. So that's why they chose to use Yugabyte. But yeah, so thanks for attending, and I think what we were trying to convey is through data modeling, like look, the data model itself is a bottleneck most of the time. If you're able to tune it, you can get much better performance. So thank you.
Awesome. Thank you, Jim and Marco. All right, folks, we have a couple of minutes for questions.
Oh yeah, questions.
And data modeling is a nice, deep, long topic. There's lots to cover, so thank you for that. Any questions, folks? Hold on.
I'm Stefan Garland. I'm from a firm. So you mentioned that the YSQL tables are index organized. Is that like clustering index and NODB or different?
It's just like that. What all that means is, yeah, it's the same storage. Like the primary key is the table, and the table is organized that way. So it's partitioned by those partitioning columns, and then ordered on disk by that. That's why changing the primary key is a little bit difficult because it has to rewrite the entire table in Yugabyte. But yeah, so the table is the primary key. It's not a separate. It's like Oracle has the same kind of concept, right?
Okay, so you get the same problems if you have a non-case sortable primary key.
What's that?
But if you have like a UUID v4 or something, it's the same problem as an NODB. Where, okay, cool.
Yeah.